magnetic flux density. So till now we have been talking about the magnetic field intensity. Okay, so now we have to see what is the magnetic flux density. So if you remember, in electrostatic fields, the electric flux density was d bar, and this was related to the electric field as epsilon E bar, right? In a similar manner, here the magnetic flux density, which is represented as B bar, this is related to the magnetic field intensity as mu into H bar. Okay, so what is mu here? This is called as the permeability of the medium. So what is the medium here? Wherever the magnetic field is present, whichever medium it is present, that is the medium that we are talking about, permeability of that medium. Okay, so what is mu? It is equal to mu naught into mu r. Mu naught is the permeability of free space. Okay, and what is mu r? This is the relative permeability of the medium. Okay, so we had permittivity in the electrostatic fields, right? Epsilon is equal to epsilon naught epsilon r. Similarly, you have here permeability, okay, which is represented as mu. Now the value of mu naught, this is equal to 4 pi into 10 to the power minus 7 Henry per meter. Now next is magnetic flux. So this is nothing but, if you take a surface area, then the flux that is passing through it is called as the magnetic flux. Okay, so magnetic flux through a surface S is given by phi is equal to integral B bar dot ds bar. Okay, magnetic flux density into elementary area integral. Okay, so the units of magnetic flux is Weber. Okay, and the unit of the magnetic flux density, this is Weber per meter square. So this is also, in the short form we write as WB also. Okay, Weber per meter square, or more commonly we write as Tesla, represented by a capital T. Okay, so we are going to use, mostly this is often used. Okay, so these are the units. Now electric fields, if you remember, they have a start and end point, right? But in the magnetic field, the magnetic field lines, they are not going to have any start and end point. They are going to end at the same starting point, right? So unlike electric field lines, the magnetic field lines start and end at the same point. Okay, so now what is the result of this? What is happening if they start and end at the same point? If you take a closed surface, okay, so if you take any closed surface, the flux, the total flux through this surface is going to be 0, because whatever is entering, it is going to again come out. Okay, so let's take a magnetic field line like this. So you can see that at one point it is entering, and at the other point it should leave. Okay, if it is not leaving, then it will be entirely inside the closed surface. In that case also, the total flux coming out is 0. Okay, so we have therefore the total flux through a closed surface. So here it is the total magnetic flux. The total magnetic flux through a closed surface must be 0. So from here you can write the mathematical form. This circle implies that a closed surface. Okay, surface integral B bar dot ds bar should be equal to 0. Okay, remember this is a closed surface integral, not all surface integral, because some surface integrals may not be around a closed surface. Okay, so this is one equation, one important equation. Now if you apply the divergence theorem, you can get a volume integral from the surface integral. Okay, so applying divergence theorem, we can get volume integral from this surface integral. Okay, so what will be the conversion here? Closed integral B bar dot ds bar, the surface, this will be equal to the volume integral divergence of the vector volume dV. Okay, so this is 0, so this will also be 0. Del dot B bar dV is 0, so from here you can get the divergence of the magnetic field vector is 0. Okay, so this is the fourth Maxwell's equation. Fourth Maxwell's equation.